Good morning, colleagues and postgraduate students and students present, lecturers that are also in our midst. My name is Osayi, Julias. My land manager is Professor Peter Osifo. We are of the Department of Chemical Engineering of our university. And the title of my presentation is Pyrolysis of South African Used Tires for Energy Recovery. This is my presentation outline. The background of the study, we all know presently that there are modern day challenges that has to do with increasing energy demand, and that is resulting from the depletion of fossil fuel sources, and it has led to lots of power crises. Though at present, we are presently in 2018, and there is projection telling us that from the year 2020 to 2030, there's going to be a large energy gap, which can be seen here. So with that forecast, there is need for us to look for means whereby we can be able to get our energy from other sources. And one of it is used tire. And the used tire presently is causing lots of problems in the environment because it is gradually increasing due to more sector embracing it in different forms of transportation. This is the common chassis we have here, even in railways, heavy-duty vehicles, airline, aviation, recreational activities, and different sector that has to do with transportation. So this has led to a generation of large volume of waste tires. So presently all over the world, the current report on waste tire worldwide is about 1 billion tons per year, with South Africa having about 142 million tons presently, based on 2008 report, and there is an increase of that with 9 million tons annually. So if this waste product is not properly managed, there will certainly be consequences, and one of it is that it can take up our available land space, and we are aware that presently in South Africa the issue of our land is becoming very, very a major point of discussion in the society. In fact, some are using it as a campaign slogan. So we don't have land, they don't have land, and now tires want to occupy the lands. That will be an issue, and it could lead to a breeding ground for disease vectors. Another potential hazard of improper disposal of this material is that in case there's fire outbreak, it's going to be very disastrous. Once it starts burning, it keeps burning. So our research motivation is now based on the continuous demand of energy, which leads to the exploration of alternative sources for energy, then the non-biodegradability of the material. It's very recalcitrant. If you bury a used tire and you leave it for the next 100 years, there might be no significant degradation that has occurred. And the major challenge that it retains its volume, it retains the shape, so it's a big issue. So the objective of this study was actually to investigate the use of pyrolysis to generate pyrolytic oil from this used tire, and at the end we carry out characterization, and then we compare the properties of the derived pyrolytic oil with that of petroleum fuels. So what is pyrolysis? Pyrolysis is the combustion of a material in an atmosphere where there's an absence of oxygen. So we're going to make use of the CVG, chemical vapor deposition reactor, and then we optimize the process because pyrolysis gives you room for that. This is one major advantage that pyrolysis gives you over other methods of combustion, like gasification, incineration. Pyrolysis can give you opportunity to optimize depending on your desired product. Are you interested in the solid, in the liquid, or in the gas? With pyrolysis you can do that. So we'll do condensation and collection of the produced liquid, which we'll refer to as pyrolytic oil. So this is a simple equation demonstrating the entire process. You feed in your used tire, and then you try and evacuate or clear the system of oxygen by making use of nitrogen, and then you're going to have three products, the char, the pyrolytic oil, and the gas. So for our research methodology, this is the experimental setup. From what you can see, the nitrogen gas is fed into the chamber that will contain the material, and then this is the collection unit. So for the characterization, these are the equipment we will use for the proximate analysis and with the experimental condition. This is for the elemental analysis, and this is also for the TGA. So when the oil was derived, we have to carry out characterization using the NM arrow. We also did characterization using the FTI arrow, and we also did characterization using the GCMS. So coming to the results and discussion from what we've gotten already, we found that with our proximate analysis, the volatile content is what we are interested in the material. We found it to be more than 50%. And when you compare it with other tires that were used in literature by other authors, it's very significant. And for such material, if you want to conduct pyrolysis on such a material, you must look out for this so that it can be able to give you an idea of the amount of liquid you're going to have at the end of the day. So the volatile content was okay, it was within specification. And then for the elemental analysis, we also looked out for the fixed carbon. It was 85%. So that's an indication that, okay, we're going to have some volume of hash that is going to come along with it. And then the sulfur content, 1.2, which is a bit not too high, but within specific range that is allowed for any liquid fuel. Then the energy, we looked at it, the heat content, 31.22 for this same tire, which was also encouraged. So for the TGA, we discovered that this is the TGA and this is the DTG. So it had two peaks, and if we are to look at the, okay, yeah. Sorry. Okay, we have two zones here. So it's telling us between these two, or this first phase, it's release of more moisture, and then the chemical or water content or bond that is within the material. And then from here to this point, this temperature, about 230 to about 520, is where you have the active zone for the degradation. So we also looked at the effect of temperature on the materials, and then we were able to use this process to optimize, and we found out that our optimum temperature is 600 degrees, and then the optimum particle size was 2 mm. Okay. Sorry for that. Okay, yeah. So this is our pyrolytic product. So we're able to get this. The solid residue was this. Then the liquid fraction, we had about 34%, and then gas fraction 17%. So we carried out characterization in terms of the fuel properties, looking at the density, the refractive index, the flash point, the pour point, the sulfur content. We all represented here and compared with others in literature. We also carried out the NM arrow, the proton and carbon-13 content. So this is the data range we obtained in terms of the shift and the percentage and what they represented. So for the FTI arrow, in order to identify the functional group, we also did that, and we found out that it has alkanes, alkanes, alkynes, and other group present in it. So we also compared this one with what was available in literature. So with our GCMS, we're able to identify the individual compounds that were present in terms of their residence time, and then the area percent gave us an idea of the concentration or the quantity that will be present in it. So from our conclusion, we're able to investigate, and we found out that the proximate and ultimate analysis results of the material showed its suitability as a feedstock for the process. And then the 3 basic products we obtained, and the mass of the liquid was 34%, which is within the range of 30 to 56% reported in literature. And then we have the amount of the gas fraction is sufficient to be a source of energy for the process when it is being recycled in. We also discovered that the GCMS result classified the pyrolytic oil to be mainly made up of aliphatic and aromatic hydrocarbons with the presence of other useful compounds such as limonene. And then the fuel properties were of commensurable features or quantity with that of commercial diesel, and it serves as a possibility to be used for combustion in diesel engine. So future work will carry out fractional distillation of the liquid to obtain distillates. We investigate the fuel consumption and fuel performance power of the distillates when blended with varied amount of commercial gasoline in a gasoline generator. So that's the sole purpose, so that we can be able to take our tire from waste to fuel for our generator. So these are our references, and I'd like to acknowledge Thermochemical Processes and Waste Utilization Group, which is the group that I belong to, and then the Research Directorate of VUT. Thank you.